Hi and welcome everyone. In this lecture, I want to go over Gram-Schmidt orthonormalization algorithm. So, my last video, I talked about orthonormal sets of vectors, and orthogonal sets of vectors. Again, to refresh our memories, an orthonormal set of vector, it's a set that has vectors that are orthogonal to each other, and each vector has a magnitude of 1. And just to let you know, the goal is to start with a base in any vector space and change that base to an orthonormal base. So let's see how that works. Now, before starting, I'm going to refresh your memories in R2 when we have two vectors, and I call them W1 and V2. We know this vector is going to be V2 minus W1. So now what's the goal? Given these two vectors, W1 and V2, we want to use these two vectors and create a new vector W2 that is orthogonal to W1. So basically, we start from here, and our goal to find a vector W2 which is orthogonal to W1 here, and I got it here for you. So how we can use these two vectors only and find that vector. Now from dot product, we know the cosine of theta, cosine of this angle between these two vectors is V2 dot W1 over norm of V2 times norm of W1. So in general, in Rn, I put the formula for you here. You have seen that before. So it's just V dot W divided by norm of V times norm of W. So let's see how we can find that vector, which is W2. Now to do that, first we have to find the vector X. What is vector X? Vector X is the projection of orthogonal projection of V2 onto W1. That's how you call it. Why? Because again, there is a 90-degree angle there, and is that if we draw a straight line from that vector, if we have any two vectors straight line, that's going to be the orthogonal projection of that vector over this vector, and that stops right there. So again, I said X is called the orthogonal projection of V2 onto W1. That's how you write it. Our goal is to find X first. So we start. So X, you just write X, the orthogonal projection of V2 over W2. Then you go to the angle. What is cosine theta? So if I have the angle theta here, cosine of that angle is going to be adjacent from trigonometry over hypotenuse. So it's just the norm of that vector over the norm of that vector. So it's going to be norm of X divided by norm of V2. You can isolate norm of X here by multiplying both sides by norm of V2. So that's what you get. But what is cosine theta? We just learned cosine theta from dot product has this expression. So you can substitute. You can say norm of X is norm of V2 times cosine theta, which is that expression. So then if you cancel V2's, you can just say norm of X is V2 dot W1 divided by norm of W1. Now our goal is to find the vector X by using the norm of X. So to find that, we have to find a unit vector in the same direction as W1, and that's just W1 divided by the magnitude of W1. So Now vector x can be written as v2 dot w1 divided by norm of w1, which was norm of x times that unit vector. And I put it for you. Here is norm of x times the unit vector in the same direction as w1, and that's going to give you the vector x. Or if you want to write it nicer, you can just say x is inside the parentheses w2 dot w1 divided by norm of w1 squared times w1. Generally in Rn, that's how you can write it. The orthogonal projection of vector v onto vector w is v dot w divided by norm of w squared times w. And again, this is times, it's not dot product. This is just a constant. We'll see how we can find that with numbers. But our goal was to find this vector. What is that vector? That vector is just v2 minus x. So it's v2 minus the projection of v2 over w1. And I wrote it here for you. So it's just v2 minus x. And now we have an expression for vector x. So you just substitute. Knowing this, let's go over the Gram-Schmidt orthonormalization algorithm. You are given a base in Rn, and that's a basis for a vector space. Any vector space in Rn. So the first process is orthogonalize. So here we're going to call W1 equals to V1. One thing I want you to notice, when we started, I did not have a V1. So we just say this vector W1, we can call that V1 equals to W1. So you can start from there. And so that's the start. You want to find W2. W2 is V2 minus, again, the projection of V2 over W1. So you can find the second vector. In general, if you want to find any Wi, it's going to be Vi minus the sum of j equals to 1 to I minus 1, and V sub I dot W j divided by V sub the norm of V sub j squared, and that's times Wj. Please be patient. You're going to see, and you go from 1, I is between 1 to m. So once you do that, then you can find W1, W2 up to Wm. So we have our W's, but we want those to be unit vectors. So you normalize every single vector in the set. So then you can call that, so S double, this is S, but our S double prime is an orthonormal set. Just to refresh your memories, S is an orthogonal set. The vectors are orthogonal to each other, but they are not unit vectors. So you have to make them unit vectors by normalizing them. As you kind of see, I went for when we are in R3, we start W1 equals to V1, W2 is V2, and that expression you are familiar with, minus the projection of V2 over W1, and that's going to give you W2, and we know that W1 and W2 are perpendicular or orthogonal. If you want to find W3, then that's going to be V3, same number, minus sum of j equals to 1 to 2, and W3 doesn't change, and you have to do j is going to be 1 first and then 2, and I wrote it here. So that can be written as, first we do it with W1, so we start with 3, then you do it with W2. So that way you're going to get your 3 vectors. This is if we have 3 vectors in the set. So now that's it. In the next video, I'm going to do some examples so you can see exactly how this process works. So please watch the next video after this one, or after watching this couple of times or 3 times, watch the next one. I'll use some vectors in R2 and R3 and do some examples for you. Thank you for watching, and have a great one, everyone.